All right, today we're going to dive into something called information theory. Now, I know it sounds a little intimidating, but stick with me because its core ideas are actually super intuitive. It all started back in 1948 with this one incredible paper by a guy named Claude Shannon. And that single paper, it really laid the groundwork for, well, pretty much everything. Your computer, the internet, all of it. So let's get started. To kick things off, let's ask a question that seems simple but is actually really deep. How much information is in a single word? Now, the answer has nothing to do with how many letters are in it. It's all about one key idea: surprise. Okay, picture this. Imagine we have a surprise-o-meter, a totally imaginary scale that goes from 0, meaning you completely expected it, to 100, which is a total shock. This simple idea is our starting point, because the more surprising a message is, the more information it's actually carrying. So let's try this out. Let's say you get a text from an unknown number, and the first word you see is thanks. You're probably not that surprised, right? Maybe a 20 on our scale. But what if that word was hippopotamus? Unless you work at a zoo, that's going to be way up there, maybe an 80. It's the context, or the total lack of it, that dials up the surprise. So now we can get a little more formal. This idea of information has 4 main properties. Number 1, likely events have low information. Finding a stapler in an office? Not surprising. Number 2, unlikely events have high information. Finding a crocodile in that same office, that's a ton of information. 3, the information from 2 totally separate events, like flipping a coin and then rolling a die, just adds up. And finally, the unit we use to measure all this is the bit. And it's important to think of a bit not as a physical thing, but just as a unit of measurement, like an inch or a pound. So if we can measure information, what can we do with it? Well, we can use that knowledge to communicate a whole lot more efficiently. This brings us to the secret of efficient codes, and our story actually starts way back in the 1840s. We've all seen Morse code, right? A different pattern of dots and dashes for every letter. But the real genius here isn't just that every letter gets a code. The magic is in which code each letter gets. There's an incredible logic behind it. And here it is, the big secret. It was Alfred Vail, who worked with Samuel Morse, who had this brilliant light bulb moment. He realized that the most common letters in English, the ones we use all the time, should get the shortest, fastest codes. And how did he figure out which letters were the most common? He did something so clever. He went to a newspaper office and just counted the little metal blocks the typesetters used for each letter. He figured the letters they used most would have the most blocks. It's like low-tech data science. And Vail's hunch? It was totally right. What's so cool about this slide is that it shows his idea in action. This is the actual count of every character in the book Treasure Island. And just look at it. The letter E and T are used way, way more than something like Z or X. This predictable pattern is the key to everything. So this leads us to 2 basic kinds of codes. You could have a fixed length code, where every single character takes up the same amount of space, say 5 units. It's simple, but it's really inefficient. Or you could have an adaptive code, like Morse, which is way smarter. It gives short, quick codes to common letters and saves the long, clunky ones for the rare letters. And this slide just illustrates the difference perfectly. If you wanted to send the name Squire Trelawney using a basic fixed length code, look how long that is. But with Morse code, which is adapted specifically for English, it takes about half the time. That is a massive, massive savings, and it all comes from adapting your code to your content. So we've been talking a lot about surprise and unpredictability. Well, the more formal, scientific word for this whole concept is entropy. It's a way to put a very precise number on just how much uncertainty, or what we don't know, exists in a system. Okay, so what exactly is entropy? Well, on one hand, it's a measure of uncertainty or disorder. A coin flip has a certain amount of uncertainty, a roll of a 6-sided die has more. But for what we're talking about, the crucial point is this. Entropy is the absolute minimum number of bits you would need, on average, to communicate the outcome of an event if you were using a perfectly efficient code. It's the theoretical speed. To get a more tangible feel for this, just think about your morning coffee. When you have your black coffee and your milk in 2 separate containers, that's a very ordered, predictable system. You know exactly where everything is. That's low entropy. But the moment you pour the milk in and give it a stir, chaos. The system becomes disordered and unpredictable. That's high entropy. Uncertainty, disorder, entropy, they're all just different ways of looking at the same thing. Okay, so entropy measures the uncertainty inside a single system. But what if we want to compare two different systems, two different worlds. That is where cross-entropy comes in. And a great way to think about it is this. It's the cost you pay for using the wrong map in a new territory. So here we have two different worlds, the book Treasure Island and the book Huckleberry Finn. And you can see, sure, they share common words like the and, but pretty quickly their important thematic words start to look very different. They represent two completely different probability distributions. So what happens when you use the wrong map? This chart shows it all. The top bar is what happens when you encode Huckleberry Finn using a perfect code that was designed just for it. But the bottom bar, that's what happens when you try to use the code that was optimized for Treasure Island. See how it's longer? It's less efficient. It takes more bits. And that extra cost, that penalty for using the wrong code, that is exactly what cross-entropy measures. So here's the official definition. Cross-entropy is the average number of bits you'd need to send a message from one world, let's call it P, when you're stuck using a code that was built for a different world, Q. It's basically a number that tells you how mismatched those two worlds are. And now we get to the big payoff. Why have we gone through all of this? Because these concepts, entropy and especially cross-entropy, are at the absolute core of how we train modern AI. In a very real way, the goal of an AI learning something is to minimize its own surprise. This slide is a perfect picture of an AI learning. The green bars represent the correct answer, the truth. In this case, it's 100% a dog. The purple bars are the AI's guesses. On the left, at the start of training, its guesses are all over the place. It's very surprised. The cross-entropy is high. The entire goal of training is to tweak the AI's brain until its predictions, over on the right, perfectly match the truth. The goal is to drive that cross-entropy, that surprise, as close to zero as possible. Now, there's one last term you'll hear, and it's called KL divergence. It's directly related to cross-entropy, but it isolates just the wastefulness. It's the pure number of extra bits you're forced to spend because your AI's predictions aren't perfect yet. It's the penalty alone. So you might be wondering, what's the difference in the real world? Well, while KL divergence is really elegant for theoretical math discussions, when you look at actual AI training code, developers almost always use cross-entropy. And the reason is simple. It gets you to the exact same results, a better trained AI, but it's just faster to compute. And in the world of giant datasets, that speed makes all the difference. And this all leaves us with a really fascinating, big picture question to chew on. If the fundamental process of an AI learning is to minimize its surprise, to make the world as predictable as it possibly can, what does that mean for creativity, for discovery? How do we build systems that don't just get better and better at confirming what they already know, but can actually stay open to genuinely new and truly surprising ideas?